enter the date, and then after this, it just kind of goes crazy. Yeah, that's not working. Today, we're finally going to show the process of how I restored Flex to working order. I went on a bunch of mailing lists in various places, and everybody said, Color Computer Archive, Color Computer Archive, it's there, it's there, it's there. Sure. So I have on the screen, yes, there is a package there that contains Flex. But what happens if you actually try to download this and use it? So this is the contents of the package. It contains something that says the master disk. This is a master disk. I don't know what all these disks are. Sure. We can just try one of them and see what happens. Okay, so I've got my X4 running here. We can try loading one of those disks in and see what happens. How about this one that says it's a master? Get a directory listing. Yeah, it says it has Flex. So let's try running it. Well, it seems to work. Let's see what happens. Disk error number 9. That doesn't sound good. Yeah, that doesn't seem to be working correctly. I really can't do anything with this. So this is what you get on the Color Computer Archive if you actually try to use what they have there. So this is another attempt that I made on real hardware that shows yet a different failure mode. Enter the date, and then after this, it just kind of goes crazy. Yeah, that's not working. In order to get this working, I had to go through a whole process of restoring the disk images to the proper formatting so that they actually work.
Warning, technical content ahead.
All right, let's get into that great technical content now. And some of you can take a nap, but not me. This is where it gets fun. All right, yes, 3. Today we have floppy talk. So I just have a diagram here where I basically show the structure of a floppy disk. You have a track, which is the red circle shown with A. You have a sector, which is literally the reason why they call it a sector is because it's like a sector of a pie, as is shown here. C points to one single disk sector. And we're not going to talk about D clusters, but this is what things look like on a disk. Of course, the disk spins round and round, so they're going around the circle. So this is the technical information about a normal color computer disk. 256 bytes on each sector, 18 sectors per track, and 35 tracks. It is normally single-sided, and it is always double density. Of course, it can be double-sided double density as well. So if we multiply this all out, we get 160 kilobytes. That number should be familiar to pretty much everybody who uses a CoCo. So the next thing we're going to talk about is we're going to go into the virtual world. As we showed in the diagram in the very beginning, the disk spins around and around, and the sectors come by one by one as the head passes them. So when we create a disk image, an image of the disk, we do the same thing. We build sectors one by one, sort of in an array, as is shown in the animation here. We have all 18 sectors that make up one complete track. So this is the very first track of the disk image. As we add more tracks to the disk image, we just continue. We continue adding sectors, and we continue adding more tracks, one after the other in a huge table, till we have the full completed disk image. So as we stated before, the full disk image is basically a big array that sits in the file on your disk, starting at track 0, sector 1, ending at track 34, sector number 18. And again, we have 160 kilobytes of data in the disk image, so this is how it lives in your hard drive for normal CoCo images. But we're not actually talking about normal CoCo images, we're talking about Flex. And this is where things get a little different. Okay, so what did we actually get from the archive? I unpacked the zip file, and this is what we got. We have this master disk that we tried before, the bottom one, master503.disk. Size seems a little strange, so it turns out that after analyzing it, what we actually have is we still have 256 bytes per sector. We have 18 sectors per track, only 34 tracks. Single-sided, single density? Huh? That's a little weird, but the math actually works out. This is the exact size that we got from the Color Computer archive. Okay, so what's wrong with that, Mikey, and why doesn't it work? Well, now it's time to do a deep dive. This is where the real floppy talk starts. The first thing that we're going to look at in our deep dive is we're going to look at the 6809 Flex adaptation guide, which contains a lot of very useful information for understanding why that disk image is a strange size, maybe, and what is it supposed to be. I definitely have some notes we'll take a look at. They talk about the Flex disk format. There is a defined format for Flex disks, which is essentially IBM floppy disk compatible, but uses 256 bytes per sector. Track 0, the outermost track, is reserved for system information and directory. The remainder is available for use of files. Okay, great. They're telling us that there's something special about track 0. So one of the things that is on this disk that I didn't highlight before is that track 0, sector 3 is called the system information record and contains data about the disk such as where, free chain, number of sectors per track, blah, 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 blah. This is actually very important. So let's take a look at what's in the SIR, system information record. System information record contains a whole bunch of useful information. For our understanding, what the most important information is byte 38 and byte 39, the highest track number on the disk. What they mean by in binary is it's not like decimal or any binary coded decimal, any strange thing. It's just an integer. Unsigned 8-bit unsigned integer is basically what this is telling us. And they have the highest track number and the highest sector number. Okay, this is very important for us to remember. So moving on, we have some information about how double-sided disks work. This is interesting for us to understand, but the disks that we have are not double-sided. One thing it is important to point out is how they number sectors in Flex, which is completely different than how they do it on a PC. Flex should treat the double-sided disk just like a single-sided one, with twice as many sectors on each track. And as I said, this is completely different than the normal PC formatting, the normal double-sided disk on a CoCo. It's completely different. I'm not going to go into the detail of that in this video. If you're actually curious to understand more about double-sided flex disks, please comment down below that you want me to go into this detail. There's one other note on the bottom of this page, which is important for us to note. Technical System Consultants format single density, single-sided mini floppy disks with 10 sectors per track. This is important for us to know. The next important thing that we need to know from the documentation is we think that the disk image that we have is double density. Double density disks are usually not really that different from single density disks, with the exception of the fact that there are more sectors per track. Technical System Consultants has altered this concept slightly. In our specifications, a double density disk usually has track 0 written in single density, while all other tracks are written in double density. So let's go back to what we just read just a moment ago. This one here. Technical System Consultants format single density, single-sided mini floppy disks with 10 sectors per track. So what this means is track 0 should have 10 sectors because it's single density. All of the other tracks on the disk are double density and they have more sectors. We think it should be 18 like a standard CoCo. So we'll get back to this in just a moment. So I'm going to show graphically what we just talked about. Track 0, we're showing here, has 10 sectors. All of the remaining tracks have 18 sectors because the first track, track 0, is single density and it can't hold 18 sectors. You can't fit it on the disk. You can only hold up to 10. The remaining tracks, because they're double density, they can have 18 sectors per track, and they do. So to sum this up, track 0 has 256 bytes, 10 sectors per track. And tracks 1 through n, all of the remaining tracks after track 0, have 256 bytes and 18 sectors per track. So this means that the size that we should actually have is 159,232, not the 157 whatever that we had before. So let's go back into our disk image and take a little bit deeper look at it. Okay, here's the disk image. So let's take a look at this with hex dump. A-C, we want to show 256 bytes, but we don't want to start at the very beginning. We want to start at sector 3 instead of sector 1. Note that arrays are normally indexed starting at 0, and so are our disk images, but sectors are normally numbered starting at 1. Normally, they could start at 0 on some systems, but normally they are 1 based rather than 0 based. So we are asking for the third sector on this disk. All right, so here's our data. We said it was byte 38 and 39. So here's 32, because this is 20. Here's 38 and 39 right here. So tracks are numbered starting at 0. Sectors are numbered starting at 1. So this means that this disk image has 34 tracks and 18 sectors per track. We know that because that's what it says right here in the system information record. So we can use this information to actually reformat the disk image with all of the information that we just learned. So how are we going to accomplish this? Well, there's a trick. Since everything in the disk image is a linear array of sectors, nobody said that we have to take every single one of them. We can actually find a way to skip the ones that we don't actually want. So I have a little demonstration of this. This track 0 is supposed to have 10 sectors. We're going to take those 10 sectors, but then there's 8 more sectors that we don't want. We don't want those 8 on track 0, so we just skip them. We skip those 8 sectors. We just ignore them. We just read past them. Read the 256 bytes for the first 10 sectors, then skip the bytes for the remaining sectors. And then for the rest of the disk, we just read all of them. And I did write a script to do this, but there's a method that you can use to do the restoration work using a tool called HXC Floppy Emulator, one of David Ladd's favorite tools, and also one of mine. I use it quite frequently, especially for this restoration project. So let's go into HXC Floppy Emulator and see what we can do. So I'm going to start up HXC Floppy Emulator. Get rid of this. Now, normally I think most people when they use this software, they use the load button. But because we need to do special formatting, we're going to use this load raw image. I'm not going to change these manually because we cannot actually set up what we need with the special track 0 formatting. So what I did, in order to skip the extra sectors, I have this XML file which describes the disk image. If you note in the name, it says padding removed. So this is the special disk image, which, as we showed a moment ago, it reads the first 10 sectors out of the disk image, and it ignores the extra ones that we do not want. And then it just continues on. We tell it to use this XML, and then we tell it to load the file that we want, which is this master disk, and then we say open. And if you notice, the little scrolly says raw image, 34 tracks, 1 slide. So this is exactly what we described earlier. Now that the disk image is loaded, let's take a look at the track analyzer. And I have the disk view shown. This is side 0, side 1, single-sided disk, nothing there. But if you look carefully at the outermost track, which is track 0, you can see that the sectors don't line up. See, this first sector here, it doesn't line up with these two. In fact, it actually takes almost twice the amount of space as the ones underneath it. So the outside track 0 has 10 sectors on it, while all of the remaining tracks have 18 sectors. Okay, we can look at this in a better view. Let's go to track number 0. So if we look at track number 0, we can clearly see that there are 10 sectors here. They are interleaved, but we have 1, 2, 3, 4, etc. 5. Here's where the directory starts. So we have 10 sectors here because the highest number on the screen is right here, number 10. As we showed before, in sector number 3, this is the SIR, we you look very carefully on the right side of the screen, I can't highlight it in this software, but line 20 hex, which is 32, the byte's 38 that we looked at before, 21 and 12, they're right there. So this looks good. So let's look at a couple of the other tracks. Yep. If you take a look at this one, it has 18 sectors, then 18 sectors on this one, and this one, and this one, etc. All the way up to track 33, which is the last track on the disk. It does not have any more than this. So it looks like we have imported this disk image properly. It has the proper formatting on track 0. So now from here, we can export this to a number of different formats, whatever formats we want actually. So I want to call it master 503. So when I release this package of disk images, the restored disk images, I think I'm only going to give out 2 different formats. I'm going to give out DMK format. We'll actually maintain all the formatting information so that it will actually work properly in XOR. Also, if I give out a DMK, you can import it into this tool and you can actually create other disk images from it. So I can go ahead and do that. If I load the DMK back in, it should look exactly like what we had before. On track 0, tracks 1, yeah, this looks the same. So now we can go ahead and export this. If we want to use a grease weasel, for example, we can export that directly to SD. Where are you? Doo-dee-doo-dee-doo. So if we want to use this on a grease weasel, we can convert this to an SCP file, like so. I'm going to call it dmk.scp, that's okay. Save. Now we have the SCP file. I can make a physical disk out of this using my grease weasel. So this was the restoration process. I have another way. I may put in another video if you guys are interested. I wrote my own script that works a little bit differently than this. Let me know if you want to see that in the comments. So to sum this up, we use the HXC floppy emulator tools to create a disk image very similar to this one. Track 0 has 10 sectors, as we saw, and all the remaining tracks have 18 sectors. In the particular case, it only has 34 tracks. I have 35 in this example. But so this is a restoration process that you guys can use if you want. I can give out the required XML files. There. Now that we have our DMK image, we can actually use it. So I'm using a version of XOR that I compiled. Run on a CoCo 2B. Load FD0. And we're going to use this master 503 DMK. Alrighty. There we are. We take a look at this. Yep, that looks like what we saw before. So if I run flex this time, maybe it'll work. There we go. We got this far before. Today seems to be the 25th. Hey, look. Instead of the errors that we got before, it looks like it's actually working. Yeah, I can cat this. Now, this is a slightly different version of Flex than I demonstrated before. Before I was showing a slightly later version, 504. This is version 503. It does not have the smooth scroll. It has tricky scroll. That wasn't a good example. Look at this. This should be a whole bunch of EQUs and other things. Keyboard layout, blah, 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 blah. But yeah, so this seems to be working. Using the HXC floppy emulator tools to convert it to a DMK allows me to actually run this properly in Flex, and I can also convert it to run on a CoCo SDC. Okay, so this is what I wanted to show you guys today. The process of restoring these disk images back to a usable state where we can use them on modern things like XOR. And these images can also be converted to SDF format to use on a CoCo SDC. That works just fine. In my next video, I'm going to show a bunch of historical artifacts, some other versions of Flex that I found, which are just basically interesting artifacts and not what I recommend people use. Alright, I think this is more than enough technical information for one video. So, bye for now.